For this lesson, we're going to talk about extrema and critical points. So extrema is talking about extreme points like a maximum or a minimum. And we have two types, absolute extrema and local extrema. So sometimes you have it where it's the highest point on an interval, the lowest point on the interval, those are the absolute extrema. Where your local extrema will be like it gets to be a rise, it may not be the highest point. So like if you had something like this, where it does, you could identify this and this as absolute extrema, assuming your interval includes them. And then you might absolute, but then you'd have, local extrema here. So we're going to talk about finding these things. Explain how to find the critical points of a function over a closed interval. Describe how to use critical points to locate absolute extrema over a closed interval. So not really a hard set of concepts, just some process to go through. So they're showing here that if you have something like a parabola, then this is your lowest point, the vertex, if it opens up. So an absolute minimum in that case. So our definition, let f be a function defined over the interval I, and let c be in the interval I. We say f has an absolute maximum I at c if f of c is greater than or equal to f of x for all x and I. So that's the highest point in the interval. And we say it has a minimum if f of c is less than or equal to f of x for all x and I. So that's if it's the lowest point. If f has an absolute maximum on I at c or an absolute minimum on I at c, we say f has an absolute extremum on I at c. Okay. So we see some cases here. This first case, you don't see any max or min. In the second case, we see this rise here. So you have a maximum. And then you have here and here and here. You have absolute max and absolute minimum in that one. For this next one, you would have an absolute maximum up here at x equals 0. But there's no minimum. And even though this does go down here, it's not a defined lowest value because it's an open interval. This has a smallest value. It also does have a largest value. And then this one has the smallest value, but it doesn't have a largest value. It just goes on forever up. So extreme value theorem. If f is a continuous function over the closed bounded interval AB, then there is a point in AB at which f has an absolute maximum over AB, and there's a point in AB at which f has an absolute minimum over AB. So now in doing that, it may have an actual a high, it gets up to a peak and then goes down, or goes down to a bottom and comes up, or it could be one of the endpoints of the interval. So you will have in your interval, closed interval, you will have some value there. So here's our maximum here, here's a maximum there, and there's a minimum there. So you have maximum is an absolute maximum. Here's another definition. A function f has a local maximum, so it doesn't mean it's the absolute. A local maximum at c if there exists an open interval I containing c such that I is contained in the domain of f, and f of c is greater than or equal to f of x for all x in the interval I. A function f has a local minimum at c if there exists an open interval I containing c such that I is contained in the domain. So same type of thing. But now we're talking about it might be a smaller interval, it wouldn't be the larger one that would have the absolute max and min. So these are called local extrema. Another definition. So let C be an interior point in the domain of f we say that C is a critical point of f if f prime at C, that's the first derivative at C, is equal to 0, or f prime of C is undefined. So this gives us different ways to find these critical values. So this happens when the slope is 0 or it's undefined. And so think about what that looks like. If you have a curve like this, right here, and right here, you're going to have slopes of 0. And so those will correspond to these extremum, whether they be local or absolute. In the Fermat's theorem, not the famous Fermat's last theorem, but if f has a local extremum at C and f is differentiable at C, then f prime of C equals 0. So being differentiable, that means you're not going to have an infinite slope. Okay. So let's use this. For each of the following functions, find all critical points. Use a graphing utility to determine whether the function has a local extremum at each of the critical points. So let's do these 3 parts to this one example. This lesson has, it's like 6 examples overall. Okay, so find all critical points. So the first thing we have is for A, we have f of x equals 1/3 x cubed minus 5/2 x squared plus 4x. So our f prime of x is going to be 1/3 times 3x squared minus 5/2 times 2x plus 4. So that first derivative is going to be x squared minus 5 plus 4. So we take that first derivative, x squared minus 5x plus 4, set it equal to 0. We have x minus 4 times x minus 1. So x equals 4 and 1. Those would be our critical points. And a graph of this would look something like, you would come up, and this is just a rough drawing. It would come up, go down, and go up again. So at 1 you'd have something, and at 4 you'd have something. Okay, for B, we have f of x equals x squared minus 1 quantity cubed. So if we take the derivative, we end up with 3 times x squared minus 1 squared times the derivative of what's inside of which is 2x. So our f prime of x is going to be 6x times x squared minus 1 squared. So 6x equals 0 means x equals 0 is a critical value. And then we have x squared minus 1 equals 0. So x squared equals 1 and x equals plus or minus 1. So these are our critical values. This one has a graph like this though. Comes down. And so at 0, obviously there's that one there. And then it has something happening here and here at -1 and 1. Okay, let's look at C. We have for C, it was f of x equals 4x over 1 plus x squared. That's not in parentheses. Okay. So our derivative is going to be low, which is 1 plus x squared times 4. D high, so minus d high. Low d high minus high, which is 4x, d low, which is 2x. All over the square of what's below. So that first derivative, if I clean that up a little bit, that's 1 times 4 is 4. Then I have a 4x squared times 4 is 4x squared. Then I have minus an 8x squared. So we're going to end up with a 4 minus 4x squared over 1 plus x squared squared. Okay. The denominator won't be 0 because 1 plus x squared is always going to be a positive over x being real. So we look at that 4 minus 4x squared, set that equal to 0, the numerator, and we'd have 4 times 1 minus x squared. So 1 minus x squared, set that equal to 0. So 1 equals x squared, or x equals plus or minus 1. This one has a graph like this. So we're seeing that 1 gets the peak and negative 1 gets that valley. Okay. Let's go on to the next one. Find all the critical points for f of x equals x cubed minus 1/2 x squared minus 2x plus 1. So our f prime of x is going to be 3x squared minus 1/2 times 2x minus 2. So it's 3x squared minus x minus 2. So we take 3x squared minus x minus 2, set that equal to 0. And we can factor this to be 3x plus 2 times 3x, not 3x, just x minus 1 equals 0. So 3x plus 2 equals 0 means 3x equals negative 2, or x equals negative 2/3. X minus 1 equals 0 means x equals 1. So those are our critical values. X equals negative 2/3 and 1. Okay, let's do another one. Uh-oh. What just happened? That was scary. It's crazy when you can just touch something and it all goes away. The next one didn't print out, so here we go. We have y equals the 9th root of x squared times 3x plus 1. So I like to write this as x to the 2/9 times 3x plus 1. So our y prime is going to be 2/9 times x to the negative 7/9. I subtract 1 from that power, times the 3x plus 1, plus x to the 2/9 times derivative of 3x plus 1 is 3. Okay, that's the product rule. Now out of this I can factor this x to this negative 7/9. So if I factor x to the negative 7/9 out, I'm going to have 2/9 times 3x plus 1 plus, and get this, if I divide x to the 2/9 by x to the negative 7/9, you subtract the powers, so that becomes just x to the 1 power. So if I distribute this 2/9 now, so I have x to the negative 7/9 times 2/9 times 3, that's going to be 6/9 x plus 2/9 plus 3x. So we have x to the negative 7/9 times, So 6/9 x plus 3x, that's going to be 27 plus 6 is 33 x over 9 plus 2/9. Okay. So we have that x to the negative 7/9. If we set that equal to 0, x is 0. And then we have this 33x over 9 plus 2/9 equals 0. That means 33x over 9 equals negative 2/9. So if I multiply by the reciprocal, 9 over 33, the 9's divide out here. I have x equals negative 2 over 33. So my critical values are x equals 0 and negative 2 over 33. Okay, pretty cool, huh? Locating absolute extrema. Now, if an absolute extremum does not occur at the endpoint, however, it must occur at an interior point, that is, within the interval, in which case the absolute extrema is a local extremum. Okay, so let f be a continuous function over a closed interval bounded by interval I. The absolute maximum of f over I and the absolute minimum of f over I must occur at the endpoints of I or at a critical point of f in the interval. So that's what we're going to check. We check for absolute extremum. We're going to look for, plug in the intervals, endpoints of the interval, and we're going to plug in any critical values. And the highest is your absolute, and your lowest is the, highest absolute max, lowest absolute minimum. Okay, so here we have the formal steps for doing this. Problem-solving strategy, locating absolute extrema over a closed interval. Consider a continuous function f defined over the closed interval ab. Evaluate f at the endpoints, x equals a and x equals b. Find all critical points of f that lie on the interval ab, and evaluate f at those critical points. Compare all values found in 1 and 2 from the location of the absolute extrema. The absolute extrema must occur at the endpoints or critical points. Therefore, the largest of these values is the absolute maximum, and the smallest is the absolute minimum. Another example. So we have, for each of the following functions, find the absolute max and min over the specified interval and state where those values occur. So we have f of x equals negative x squared plus 3x minus 2 over 1, 3. So let's look at a here. Our f prime of x is going to be negative 2x plus 3. So negative 2x plus 3, set it equal to 0. That's negative 2x equals negative 3. X equals 3 halves. So I'm going to look at f of 1, f of 3 halves, and f of 3. So let's see what I have here. I found f of 1 to be 0, f of 3 halves to be 1/9, and f of 3 to be negative 2. So our absolute max is at 3 halves 1/9, and our absolute minimum is at negative 3, negative 2. And that's it. Let's do the part B. Come over here and start writing it. Okay, so for part B, we have f of x. Maybe I can't go over there and start writing it because my bad screen. F of x equals that x squared minus 3x to the 2/3. So f prime of x is going to be 2x minus 3 times 2/3 x to the negative 1/3, which would be 2x minus 2x to the negative 1/3. So from this, I guess we'll set that equal to 0. Negative 1/3. Set it equal to 0. I could factor out that x to the negative 1/3, or 2 times that in fact. And I'll be left with an x to the 4/3, because that's x to the 1 divided by x to the negative 1/3. You subtract the powers, it's 1 minus the negative 1/3, it's 4/3, minus 1 equals 0. So 2x to the negative 1/3 equals 0 means x is 0. And x to the 4/3 minus 1 equals 0 means x equals 1. So what we're going to check for are f of the endpoints are 0 and 2, 0. Now we're going to look for f of 1, and then we're going to look for f of 2. So f of 0 is 0, f of 1 is negative 2, I just plug these in the calculator, and f of 2 is negative 0.762. So we have our absolute max and our absolute min. That's at 0, 0. That's at 1, negative 2. Okay. Let's go on. Do a couple more of these. Find the absolute max and absolute minimum. So same type of thing. Our f prime of x is going to be 2x minus 4. So 2x minus 4 equals 0 means 2x equals 4 and x equals 2. So we'll look for f of 1, f of 2, and f of 4. So f of 1 is 0. F of 2 is negative 1. And f of 4 is 3. So this is our absolute minimum and absolute maximum. So hope you see the process. The big thing is using those calculus skills to take the derivative and then set that derivative equal to 0 and find the zeros. So we use algebra skills there. Last problem, didn't print out. So this one has g of theta equals 4 theta minus 5 sine theta. And this would be in radians then. So our g prime of theta is 4 minus 5 times cosine of theta. The interval they give us is from 0 to pi. So let's set that 4 minus 5 cosine theta equals 0. That means 4 equals 5 cosine theta. That means cosine theta is 4/5. So that means theta would be theta is going to be cosine inverse. So theta would be 0.64350. Oh, sorry, 011. Then we have, so g, we're going to check the endpoints, g of 0, check the critical point, g of 0.6435011, then g of pi. So g of 0 is 0, g of 0.6435011, which was that cosine inverse of 4/5. That comes out to be negative 0.4259956. and g of pi is 12.566. So from that we have our absolute min and our absolute max. That's it. Okay, hope this section goes well for you all. See you at mean value theorem.